So today let us start with this dynamic analysis of slider crank mechanisms. Right, so here we will see what are the different forces acting when a slider crank mechanism is under working condition. So in order to have idea about the forces acting on different component, first we have to have idea about the displacement, velocity and acceleration of different components, right? So if we want to analyze this velocity and acceleration of a piston analytically, then first we can start with the displacement by having analytical relationship of the displacement with this theta and length of connecting rod L and crank radius R. Right, so let us first see how we can come up with the displacement of piston. Right, so if you see in this figure here, the piston has moved from position B to B1, right? So when piston moves from position B to B1, you have that distance traveled by piston is given by this BB1, right, or you can say B1B. So if you see the figure clearly, this B1B or BB1 can be represented or given by this BO minus B1O, right? You can see here this distance BB1 can be given by this BO, right, minus this B1O, right? So this is how you can have idea about the distance traveled by piston, this BB1. So if you observe this figure, then here L is length of connecting rod, as you can see in the figure clearly, right? L is the length of connecting rod and R is the crank radius. So if we consider B as top dead center, then at particular point B, this distance OB can be given by L plus R, right? So this distance can be given by L plus R. Now if you see this B1O, then that B1O can be represented by this L cos beta and R cos theta, right? So I can write that B1O as L cos beta plus R cos theta, right, from the geometry of the figure. Now if we define that obliquity ratio N is equal to L by R, as we have seen in the previous lecture also, while we have seen that turning moment versus crank angle T theta diagram, in that we have seen that what is the turning moment, where we have seen that piston effort is there in the action for this or it is responsible for this turning moment. So in that equation I have defined that N or obliquity ratio is equal to L by R, where L is length of connecting rod and R is crank radius. Now if you consider this, then you can rewrite the above equation by putting L is equal to NR. So your equation will be like this: NR plus R minus you will have NR cos beta plus R cos theta, right? Now if you take out R from all the terms, then what you will left with is N plus 1 minus N cos beta plus cos theta, right? Now if you are interested in finding the value of this cos beta, then if you go by the geometry of the figure, then cos beta can be given by 1 minus sin square beta. Under root of 1 minus sin square beta will give you the cos beta, right? Now if you see the figure clearly, then this sin beta in this triangle A1 and B1 is given by y by L. So you can write that 1 minus y square by L square from the figure, right? Now if you see the triangle AOA1, then your y can be also represented with R sin theta. So now what you can do is, in place of y you can write R sin theta, so R square sine square theta upon L square. Right. Now as you have defined this n is equal to L by R, now if you take that R in the denominator, then you can have that 1 minus sine square theta upon n square. Right. One second, let me clearly write this. Right. So it is 1 minus under root of 1 minus sine square theta upon n square. Right. So if you further simplify it, then your cos beta can be given by this 1 upon n under root of n square minus sine square theta. Right. So one second, let me check, is there any message? Okay, yeah. So here cos beta is equal to 1 upon n under root n square minus sine square theta. So what you can do is you can put that value of cos beta in the above equation of, or above expression of s, right? So x is equal to now r n plus 1, right, minus this n square under root of n square sine square theta, n square minus sine square theta, sorry, right, plus cos theta. That n will be cancelled, right? So this is how you will find your equation of displacement. If you further rearrange, then what you will get is this as 1 minus cos theta plus n minus under root of n square minus sine square theta, right? So now this is actually the equation for displacement of your piston, right? So once you get this equation for displacement of piston, if you consider that length of connecting rod is greater than r, right, then what will happen is n square will be very large, right? N square will be very large in that case. So if you have n square is very large in comparison to this sine square theta, then here n square will become n, and n will cancel out. So your equation will be simplified to x is equal to r in bracket 1 minus cos theta only, right? So this is how you can simplify it if your length of connecting rod is very higher or very larger than the length of the crank. So this is how you are having this what we can say, this displacement of your piston. Once you have displacement of piston with you, then you can go for finding the velocity easily, because velocity is nothing but the displacement change in displacement, right, with respect to time. So once you have that dx by dt, you can rewrite it as dx by d theta and d theta by dt, right? So if you differentiate this, right, d theta by dt will simply be omega, right? Your d theta by dt will simply be omega. Now if you differentiate this x with respect to r, that above equation which we have written, right, not this simplified, but the above equation which we have written, if you simplify it, or sorry, if you derivate it with respect to theta. Yes,
sir, your voice is not audible.
so is it for everyone? Voice is not audible?
So you're audible, but strength is very low, sir.
Is it everyone is facing the same issue, or only few of you are experiencing this? So you please check, right? I guess almost many of you are getting it clearly. Okay, thank you. Yes, so let us go ahead with this differentiation of this displacement with respect to theta. So what is your x? I can rewrite here, right? You can have this r 1 minus cos theta, right, plus n minus n square minus sine square theta raised to 1 by 2, right? So this is how you can have your x, and which needs to be derivated or differentiated with respect to theta. So if you differentiate it, then differentiation of 1 will be 0, differentiation of minus cos theta will be minus sine theta, right? Like this. Then when you go for this, it will be this 1 by 2. Sorry, for this n it will be again 0. For this minus n square minus sine square theta raised to 1 by 2, it will be, here it was minus, right, because plus n is 0 anyway. So minus this 1 by 2 n square minus sine square theta. This 1 by 2 minus 1 will be again minus 1 by 2, right? And when you go for differentiation of that minus sine square theta, it will be minus 2 sine theta cos theta, right? So this is how you will have your differentiation, right? So once you write this differentiation, and when you simplify it, what you will get is omega into r in bracket sine theta plus the sine 2 theta divided by under root of n square minus sine square theta. This is the velocity of piston, right? So you can have this velocity of piston, right, can be calculated from this equation. Here also, as you have simplified the displacement, you can also have this simplified velocity in case of n square is very greater than sine square theta. So if n square is very greater than, or it is having large value in comparison to sine square theta, then you can simplify this velocity with omega r sine theta plus sine 2 theta by 2n, right? So this is how you can simplify your velocity, right? So once you are done with this velocity and acceleration, the next is you have to calculate the acceleration of piston, right? So piston's acceleration can be given by this dv by dt. Again you can write it with chain rule, like dv by d theta and d theta by dt, right? So again, when you derivate velocity with respect to theta, and d theta by dt will be omega again. So when you again give simplification and do the calculation or do the simplification, then you will come up with r omega square cos theta plus cos 2 theta by n, right? So this is how you can have your acceleration. Here also, if L is greater than R, then it can be simplified to A is equal to R omega square cos theta, right? So this is how you are having the velocity and acceleration of your piston. Now once you are done with this velocity and acceleration of piston, the next is you can think of having this angular velocity and angular acceleration of the connecting rod, right? So as you know from the geometry, again you can see this figure over here, right? So if you see here, y is actually in the both the triangle, right? AA1B1 and AA1O. So if you consider different triangle, then y can be given by L sine beta as well as R sine theta, right? So both can be written for R, right? So here what you can do is you can write that y, this y can be written as L sine beta as well as R cos theta, right? So from this, what you can write, sine beta can be given as sine theta, right? Sorry, here L sine beta and R sine theta. Sorry, as we have seen from the geometry, y can be written with L sine beta or R sine theta. Right, so once you have this, then you can write this sine beta is equal to sine theta by n. Why? Because this n is equal to L by R. Right, so sine beta can be written as sine theta by n. Now if you differentiate this equation, then it will give cos beta dv by dt is equal to cos theta by n d theta by dt. You have differentiated this equation with respect to time. So when you do that, you will find this, right? Now here dv by dt is nothing but angular velocity of connecting rod. dv by dt is omega c, and this d theta by dt is angular velocity of crank. So omega c can be then written as omega cos theta divided by n, and this cos beta we have already calculated in the previous calculation, that it is given by 1 upon n under root n square minus sine square theta, right? So if you write like this, then your omega c can be written as omega cos theta upon n square minus sine square theta, right? So once you have calculated your omega, then again it is just a matter of differentiating your omega with respect to time in order to get angular acceleration of your connecting rod. So if you differentiate this d omega c by d theta into again d theta by dt, right? So if you again differentiate the angular velocity of connecting rod, then you can come up with the final equation as minus omega square sine theta, right, n square minus 1 upon n square minus sine square theta plus to 3 by 2, right? I am not doing this intermediate
थोड़ा सा ऊपर करना
steps.
है सर, थोड़ा सा स्लाइड को अप करना.
Yes. Okay. Okay.
यस सर.
So now can I move to this one? So here I have not written the intermediate steps, but you can follow the intermediate steps and you will reach to this angular acceleration of connecting rod, right? Okay, so once you are done with this, then we can see the various forces acting in this piston and what we can say in this engine, right? So here in this slider crank mechanism, what are the forces acting? We can see I have mentioned this forces as piston effort, then force along the connecting rod, then thrust on the sides of cylinder, then crank effort and thrust on bearings, right? So you can see here piston effort is mentioned with this notation F. This particular force along connecting rod is given by Fc. Then thrust on the sides of the cylinder is mentioned by this Fn. Then crank effort is given by this Ft, right? And this thrust on the bearing is we will see it can also be this mentioned by Fr, right, as it is mentioned over here. So we will see what are the different forces acting in this mechanism, right? So if we see one by one, then let us start with this piston effort, right? If you see this piston effort, then there is a pressure, right? Whenever that combustion of fuels takes place, there is a pressure on the side, on both the sides of piston. Here you are having that pressure acting on this side. Similarly, here also some of the pressure will be there inside the cylinder, and at both the sides piston is having area, let us say A1 and A2 respectively, on this side, on the upper side or on the side of combustion, right, and on the opposite side of that. So if you take that pressure as P1 and P2, and similarly area as A1 and A2, then that force acting on piston due to this pressure is P1 A1 minus P2 E2. That is the force acting on piston due to this pressure on both the sides of the piston, right? Now once this force will start moving the piston, there will be inertia force, right, which will come into picture. That inertia force is given by this m into a, right, acceleration. So this acceleration is what we have derived earlier. So if you remember, this acceleration we have derived is r omega square cos theta plus cos 2 theta by n, right? So this I can actually write as Fi also, right, to avoid any confusion. So this is inertia force, right? Fi is equal to mass into acceleration. So if you see, if you try to write the net force acting on this piston, that is this force due to that pressure minus this inertia force. This is how you can calculate the piston effort, right? But apart from this, what happens is sometimes if you consider the frictional force, then that frictional force will also be subtracted from this this force due to pressure on the piston, right? As inertia force is acting opposite to it, the frictional force will also act opposite to it. Now this is how you can calculate the piston effort. But in case of vertical engine, what happens is you will have that force component, or let us say weight force mg, right, that is also acting in the direction of motion of piston. So in that case, this Fp, right, will be supported by this weight force of piston mg, right, and again this inertia force and frictional force will be opposite to these forces. So this is how you will come up with piston effort, right, finally with this particular forces, right? Now once you are done with this piston effort, then you can think of this force along the connecting rod. So if you think about the force,
कर देना स्लाइड अप कर दो आप.
1 second.
ओके सर, ओके.
Okay, so now you can think about the force which is acting along the connecting rod, right? So if you think about the force along the connecting rod, right, if you think about the force along the connecting rod, then from the geometry of the figure, I am again showing you that figure. From the geometry of the figure, this F is equal to Fc cos beta, right? From the figure it is clear that F is equal to this Fc cos beta. So in short, you can calculate your force along the connecting rod from the piston effort if you know this angle beta, right? So this Fc can be given by F upon cos beta. Similarly, that thrust, right, on the cylinder wall, can also be calculated from piston effort, right? So if you see that figure, it will be clear that this Fn is nothing but F sine beta. I am showing you the figure. So if you see this here, this Fn is nothing but this what we can say F upon sine beta, or you can say this Fn is equal to Fc sorry, this thrust on the cylinder wall can be given by Fn, which is represented with Fc sine beta, right? Fc sine beta is here you can see, right? This is Fc and this is Fn, which is vertical component. So this vertical component can be represented with Fc sine beta, right? So here, sorry, actually it is Fc sine beta. So Fn can be
सर वो क्या
represented
लिखा था
with,
तो फोर्स
sorry,
फोर्स अगेंस्ट वाला जो अभी लिखा था ऊपर जो लिखा हुआ था फोर्स अगेंस्ट
this is force along
हाँ
the connecting
ये
road.
फोर्स अलोंग द कनेक्टेड रोड यहाँ से लिखो
Okay. So here actually this the thrust on the cylinder walls can be given by Fc sine beta. Now if you further want to classify it and want to write it in terms of piston effort, then you can write this force along the connecting rod in terms of that piston effort. So Fn can be written as F upon cos beta into sine beta. So if you write like this, then finally you can write your thrust on the cylinder as F tan beta, right? So you have written this force along the connecting rod also in terms of piston effort, similarly thrust on the cylinder wall also in terms of piston effort, right? So this is how you can calculate the thrust on the sides of the cylinder wall. Now if you are supposed to, can I go down? Hello, can I go down for crank effort? Okay, let us go for that.
सर स्लाइड आप लेने के अब लेने से पहले बता दे करो सर सर नीचे करना सर थोड़ा सा
That is
और नीचे करो बस हो गया सर स्क्रीनशॉट लेना था
okay. So now let us move to the crank effort, right? So if you see crank effort, so crank effort is Ft, as we have seen earlier, right? So if you equate the turning moment Ft into R, right, to this Fc into R sine theta plus beta. Now why we have equated this, you can have idea from the geometry. I am taking it to geometry. So here this Ft into R, right, see here Ft is that force and this R is a perpendicular distance from this particular pivot O. So turning moment due to this Ft, right, will be Ft into R will be similar to this Fc, right, into that perpendicular distance from this Fc. Perpendicular distance from this Fc will be R sine theta plus B, as it is mentioned here, right? So that is why Ft into R will be similar to Fc into R sine theta plus B, because both are the turning moment, right? And turning moment will be same whether we will calculate it with this crank effort or with this force along the connecting rod. So that Ft into R will be similar to this Fc into R sine theta plus B. Now if you give simplification, then what you can do is, in case of this crank effort, when you give simplification,
सर फिर दोबारा ऐसे कर दे सर स्क्रीनशॉट नहीं ले पाया सर
see actually that slide though we have already seen earlier, na? This geometry slide we have seen earlier also, this slide, right? Okay, hello, is it okay?
अब लेना सर
Okay, now yes, so again if you now come to this, then Ft is now can be written as Fc sine theta plus B. Now as I have told you earlier, if you want to write this Ft also in terms of piston effort, then Ft is equal to F upon cos beta sine theta plus B, right? So this is how you can calculate crank effort, right? And finally the thrust on the bearings, that also you can calculate, right? Thrust on the bearings. So thrust on the bearings, this Fr can be calculated as Fc cos theta plus b, right? So from the geometry it will be clear that Fr is equal to Fc cos theta plus b, where again Fc can be written as F upon cos beta, right? So this is how you can have forces acting on your engine, right, while it is under working condition. So this is how you can calculate thrust on the bearing with the piston effort and the angles, right, that angle beta and theta. So once you have this engine force analysis, you can also have idea about the turning moment on crankshaft, which actually we have written that Ft into R. So if you remember, Ft we have written as F upon cos beta into sin theta plus beta, right, into R. So now this can be written as Fr upon cos beta, right? If you expand sin theta plus beta, then you can write it as sin theta cos beta and cos beta sin theta, right? So if you write like this, then you can further simplify it as sin theta plus, sorry, here it will be cos theta sin beta, here it will be cos theta sin beta, right? So what will happen here, this cos beta will cancel out, and here you will have this cos theta into this sin beta and divided by cos beta. Now as you have seen earlier, that the sin beta can be written as the sin theta by n. Similarly, this cos beta can be written as 1 upon n square minus sin square theta, right? So if you further simplify it, then this n will be cancelled out and you can write it as Fr sin theta plus, if you multiply and divide by 2, then 2 cos theta sin theta will give you sin 2 theta, and divide by 2 into this under root of n square minus sin square theta. So this is how you can have your turning moment, and this, from this we have started our last session, right? The turning moment is Fr sin theta plus sin 2 theta by 2 under root n square minus sin square theta. So this is how you are having a turning moment on crankshaft, right? So should I change it now?
Yes, sir. Yes, sir.
Okay. So now once you are having this idea about the various forces acting on it and this turning moment acting on it, right, then what we can do is we can go for some of the questions from the same area in GATE, right? So here this is a question from GATE 2014 session 3, that a slider crank mechanism with crank radius 60 mm and connecting rod length 240 mm is shown in figure. Now the crank is rotating with a uniform angular speed of 10 radian per second counterclockwise, right? So here this crank is rotating counterclockwise. Now for the given configuration, the speed in meter per second of the slider is. So can you try and type in your answer in the chat box? Is it possible? Hello?
Yes, sir. Just give some moment to
Yeah.
calculate it.
Yeah, please calculate.
.619.
Okay, correct. Anyone else is getting the same? Someone is asking regarding the slide. Actually, I am sharing the link. 1 second. One second, I am sharing the slides. I have shared that drive folder with you, which is having this notes. I'm checking whether it is working or not. So you can have that slides with you now. I will also upload today's slides. Someone can check. Access is not there.
Yes, sir. No access.
One second. Let me check. Now can you check whether you can access it or not? Please check. Can you check?
Yes, sir. It is accessible now.
Okay, now is it okay, right?
Yes, sir.
Okay, now please tell me, 2 of you has written the answer. Anyone else is there with the same answer? Hello? If you are getting the same answer, then please update in the chat box.
Yeah, already done.
Okay, let me also go
Sir,
through this.
sir, I am getting 41.15.
Let me then help you out in that one. Right here, what given is R is equal to 60 mm, right, and L is equal to 240 mm. So your N will be L by R will be 4, right? So, and omega is mentioned as 10 radian per second. So from this given data, your this what we can say, this Vs that velocity of that slider which we have derived is omega r sine theta plus sine 2 theta by n. Now here if you see your actually theta, if you consider this triangle, right, and you consider this as theta, then your tan theta can be given by L by R, which is nothing but n, right? So if you consider this theta, then tan theta is equal to L by R, that is nothing but n. So your theta is tan inverse n. N is 4, right? So your theta is tan inverse 4. So it is around 75.96. So now when you have all the data for calculating this speed with you, like theta you are having it, omega is already there, r is also there, n also is defined as 4, right? So when you are having all the required data with you, and if you will put all the data in the above equation, you will come up with the value around this 0.617 meter per second. So now is it okay?
Yes, sir.
So let us go ahead. Yes, the next one. So the next question is from GATE 2015 session 2. In a certain slider crank mechanism, lengths of crank and connecting rod are equal. If the crank rotates with a uniform angular speed of 14 radian per second and the crank length is 300 mm, then the maximum acceleration of the slider is. So can you try this question? Hello? Hello?
Yes, sir.
Please try and tell me what you are getting. So maximum acceleration will be at theta is equal to 0, right? I'm giving you the hint, right? So now you can calculate and type in your answer in the chat box. You can use that equation which we have derived for the acceleration of piston or the slider.
Done, sir. 117.619.
Correct. So every one of you are getting the same answer?
Sir, since by differentiating the acceleration, we can also get a expression like cos theta equal to minus 1 by 4 can also be maximum.
What are you telling? Please can you repeat it?
Sir, on differentiating the acceleration equation, yes, sir, theta equal to 0 we are getting like 4 cos theta plus 1 equal to 0.
Okay. See, actually this if you are differentiating, then cos theta will be minus sin theta, yes or no?
Yes, sir.
Right. And cos 2 theta by n will be minus 2 sin 2 theta, yes or no?
Yes, sir. Yes, sir.
So if you further, you have done like this only or something else?
Yes, sir. In that way only, sir.
So in that way, if you further proceed, then sin theta minus 2 sin 2 theta will be equal to 0. Yes or no?
Yes, sir. Yes, sir.
So if you further simplify, then sin theta will be equal to 2 sin 2 theta, and sin 2 theta will be again 2 sin theta cos theta. So sin theta will be cancelled out from each side. Yes. right, like that you have proceed,
हाँ sir जी sir.
right? Hello.
हाँ सर मतलब उसी तरीके से किया तो सर cos theta equal to -1/4 आ रहा था एक.
It cannot be -1/4, I guess. Check your calculation again.
Sir, it is.
Okay, because on both the sides you are having that minus, right? Cos theta is minus sin theta, and that cos 2 theta is minus 2 sin 2 theta, like that. Okay. So if you go for, actually then that n will be multiplied with that sin theta also, right? Before going for.
Sir, since n is 1, it is given, sir.
Yeah, n is 1, right, correct. It is mentioned already, yes. N is 1. Then this minus sin theta minus 2 sin.
So I guess 2 is being missed in the velocity equation. There is 2 in the denominator in sine 2 theta by 2n. You also did not mention in the previous example.
Oh, is it? 1 second. In case of velocity it is 2n, na? In case of this acceleration it is n only.
No, yes.
Right. So here actually it is minus sin theta is equal to 2 sin theta cos theta, right? So in that case this will be equals to then minus 1 by 2, no? Minus 1 by 4, how are you getting minus 1 by 4?
Sir, it's -1/4. Because the differentiation of cos 2 theta is 2 sin 2
Oh
theta minus 1.
yes, correct. Okay, so if we go by that, then we are having this cos theta is equal to minus 1 by 4. Okay, that's true, but actually in case of this engine analysis, when we are having that theta is equal to 0, at that point we are having that maximum acceleration. So that is why I have considered this theta is equal to 0 for maximum acceleration.
Sir,
Right.
since after finding the second derivative of this expression,
Mhm.
I am also getting a negative number, which means that is also a maxima. It may be possible that at theta equal to 0, it must be the global maxima.
Yeah.
ये हो सकता है.
Yeah. So that is why we are taking this theta is equal to 0 for maximum acceleration, right?
Okay, sir.
So if we take that theta is equal to 0 for maximum acceleration, then in that our equation r omega square, this cos theta plus cos 2 theta by n. When you put this theta is equal to 0, you will find r omega square 1 plus 1 by n. You are having n is equal to 1, so ultimately it is 2r omega square. You are given crank length and this angular acceleration both, so when you will write the values of that, you will find that it is coming around 117.6 meter per second square. So is it okay?
Yes, sir.
Okay, so for the next question,
Sir, velocity is maximum at theta equal to pi by 2.
that we have to again go for the same way as you have calculated in this particular case, right?
Okay, sir. Yes, sir.
Okay, so now GATE 2016 session 1, it was asked that a slider crank mechanism with crank radius 200 mm and connecting rod length 800 mm is shown. The crank is rotating at 600 rpm in the counterclockwise direction. In the configuration shown, the crank makes an angle of 90 degree with the sliding direction of the slider, and a force of 5 kilonewton is acting on the slider. Now neglecting the inertia forces, the turning moment on the crank, right, in kilonewton meter is, so you have to calculate the turning moment. So can you try this
Yeah,
question?
yeah.
So please try.
That answer would be 1.
It is easy, right, because everything is
Yeah.
with you, everything is given.
The answer would be 1.
Correct. So but every one of you are getting the answer.
Sir, how fastly he is able to calculate? Sir, please also tell us.
See, because it is
Actually,
very
it has a shortcut trick. If you apply T equal to F into R,
yes,
then
that is only the way, right? Ft into r is only that moment, right? And ft is anyway given as f upon cos beta, right? And here this ft, this angle is 90, right? So theta plus beta will be converted into cos beta. Sin theta plus beta will be converted to cos beta. That is why it is easier. F is given, R is with you, right? 0.2. So it will be 1 kilonewton meter. Right? Ft is F upon cos beta sin theta plus beta. Here theta is 90, so sin theta plus beta will be cos beta. So cos beta will directly cancel out. So it is very easy question. All of you have got this? Hello?
Yes, sir. Yes, sir.
Okay. The next is from GATE 2017, session 2. In that, what they've asked is, in a slider crank mechanism, the lengths of the crank and the connecting rod are 100 mm and 160 mm respectively. The crank is rotating with an angular velocity of 10 radians per second, right, counterclockwise. Now the magnitude of linear velocity of the piston at the instant corresponding to the configuration shown in the figure. So velocity you remember, right? Hello? We have derived that equation for velocity. You can use it. Yes.
Sir, isn't it did on the previous problem like the same like this one?
It is also similar, but here what they have asked is different, right? Previously they have asked turning moment. Here they are asking for the velocity of the piston. So here you have to calculate velocity of the piston, which we have derived, right? Can anyone tell me the equation? Any one of you? Any one of you can unmute and tell?
Yeah. Sir, could we apply this by using I-center or like vector analytics?
That can also be doable, I guess. If you try, then you can go by that way.
Sir,
also.
is the answer 1 meter per second?
Yes.
Yeah, 1 meter per second.
Correct,
Yeah,
correct.
definitely.
So the equation which we have derived, you can write that equation r omega sin theta sin 2 theta by 2n, right? So sin 2 theta by 2n will be equal to 0 because here sin 180 will be there. So you will left with r omega sin theta, and sin theta is 90. So r omega only. R is 0.1 meter and omega is given as 10. So you will have this 1 meter per second. So is it clear?
Yes, sir. Yes, sir.
Okay, so let us go to the next one. So next is from GATE 2018 session 1. A slider crank mechanism is shown in the figure at some instant. Now the crank angle is 45 degree and a force of 40 kilonewton is acting towards the left on the slider. The length of the crank is 30 mm and the connecting rod is 70 mm. Now ignoring the effect of gravity, friction and inertial forces, the magnitude of the crankshaft torque in Newton meter needed to keep the mechanism in equilibrium is, right? So what you have to calculate is the magnitude of the crankshaft torque, right? So you can start calculating. You can try it, right? Hello.
Yes, sir. Yes, sir.
Yes, sir, yes.
So
1.13 or like that.
1 point, yes, it will be in that range only. So let others also calculate. धीरे धीरे ही बोल रहा हूँ, बाद में हम करवाएंगे, आप काहे कर रहे हो, ये बोल रहा हूँ. मतलब नारिश खतरनाक. So every one of you got the answer?
Sir, 1.118.
Sorry, 1.118. It is coming around that only. So here, if you see, what they have provided is 30 mm of this crank length, then 70 mm of this connecting rod length, right? So if you consider this as beta, right, let us say, and if you consider this as right, theta or beta, whatever, but this angle and this angle if you consider, and then as we have equated this y, right, it is equal to this 30 sine theta equal to this 70 sine beta. So in this, I guess they have provided the crank angle, right? So this crank angle is provided, so this 30 sine 45 maybe equal to this 70 sine beta. So if you further simplify it, you can calculate beta, which will come around 17.64 degree, right? Now if you see here from the figure, this Fc cos beta is equal to crank effort, which is 40 Newton, right? So if you calculate this Fc from that cos beta we have already calculated, so you will find that Fc is equal to 41.9737 Newton, almost it will be equal to this. So once you have this Fc, which is force along the connecting rod, then what you can do is you can calculate this Ft. This Ft is Fc sine theta plus b, right? So you have value of theta and beta both, and you have calculated Fc also. So this Ft will be around 37.2785 Newton. Once you have Ft with you, you can easily calculate this particular torque, right, or turning moment, Ft into R. R is there, right, 30 mm, so you can convert it into meter, that is 0.03 meter, and when you multiply it with this 37, you will come up with this 1.1183 Newton meter, something like this. So now everyone is clear? Hello?
Yes, sir.
Okay.
Yes, sir.
Okay. So now after this dynamic force analysis, let us go to the next topic, that is of governor. So last time we have seen that flywheel, right? So as yes, so as you know, during a cycle in your engine, torque is not generated equally during the whole cycle or during the revolution of your that what we can say crank. So the flywheel is acting as a reservoir, and it is storing the torque when it is in the excess, and it is providing the torque when it is not in the required amount. Similarly, governor is also doing the same, but it is actually regulating the speed, right, by increasing or decreasing the supply of fuel, right?
Fuel, yeah.
Sorry.
Actually, I was telling that it also maintain the supply of the fuel.
Yes, it is going to do so by maintaining the, or we can say regulating the fuel supply, right? So actually governor's function is actually intermittent function, while that flywheel has continuously perform in, because during each cycle it has to store the energy and it has to release the energy, while for governor it is not so. Governor will only come into picture when there is a change in load, right, which is acting on your engine. There will be a particular equilibrium speed, right, at which engine is designed to run, right? So before going into this, the types of governor are generally given as centrifugal governor and inertia governor. Right. So this is a centrifugal governor. So if you see here, you are using this fly balls, right? This fly balls are attached, right, to the what we can say this particular engine shaft through this bevel gear. So what will happen when engine speed is going to change, this particular fly ball is also going to experience the change in the speed. Once this fly balls are going to experience the change in speed, there will be a difference in the centrifugal force acting on it, right, mr omega square. So if the speed of the engine is increasing from the equilibrium speed, right, then this fly balls will go out or go up, right? It will go out and go up in case of increase in the speed. So when this happen, when it will happen, when the load is going to decrease, at that time speed is going to increase. So when it happens, this particular fly balls are attached to sleeve, which is attached to a throttle valve in the fuel supply system through a bell crank lever. So when this fly balls will move upwards and outwards, this sleeve is going to have upward motion, and while sleeve is going to move in the upward direction, this throttle valve on the fluid supply system will tends to reduce the supply of fuel because the speed of engine has increased. So that is how the fuel supply will be reduced in order to again come back to the normal position, right? Now if you think in opposite manner, that if the speed of the engine is going to decrease, then when it will happen, when load is going to increase, that speed will decrease, and when speed is going to decrease, this fly ball will come downwards and inward. And when fly ball is going to come downwards and inwards, the sleeve will move again downward, and this throttle valve will be opened in order to supply more fuel. So this is the basic thing for operation of a governor, which is going to regulate the fuel supply, right? So there are this, as we have seen, that a centrifugal governor and inertia governor. So here what we have discussed is the centrifugal governor. In inertia governor, actually the angular acceleration and deceleration will also going to take part in deciding the fuel supply, right? So in that case, actually rate of change of speed is going to be monitored when you are using this inertia governor, right? While in case of the centrifugal governor, only that magnitude of speed or change in speed or range of speed is going to be important, right? So
Sir,
yes,
sir, please again tell the difference what you were telling about.
see here, in case of centrifugal governor, only this fly balls, right, which we have used, are going to govern the what we can say throttle valves opening and closing, right? But in case of inertia governor, this angular acceleration and deceleration of a disc is also going to take part in deciding the movement of the sleeve, right? So in addition to the flyball's mass, inertia of the disc on which those flyballs are attached are also going to take part in deciding the opening and closing of this throttle valve, which is supplying the fuel.
Sir, is the left hand side figure is for inertia governor?
No. Left side figure is for vote governor only, right? Right. So this is vote governor only. So in this vote governor, as you can see, this two fly balls are there, right? And this is the height of the governor. H is termed as the height of the governor, and this R is the radius at which these fly balls are, right? And this T will be the tension in that particular link, right? So if you think of the what we can say forces acting or the equilibrium of forces at this fly ball, then you can see that here this T cos theta can be mentioned as mg, or can be equated to mg, right? Because forces acting in the vertical direction will be equal and opposite, because we are assuming equilibrium, right? So this will come from the sigma fv is equal to 0. Similarly, if you go for sigma fh is equal to 0, then you will find that T sin theta is equal to mr omega square, right? Where this m is mass of this fly ball, h as I have already mentioned, height of the governor, right? And mg is the weight of this ball, and omega is the angular velocity at a particular instant, right? And T is the tension in the arm, as we have already mentioned, right? So this is how you are having this T cos theta is equal to mg, and this T sin theta is equal to mr omega square. So if you take ratio of this both equation, then you will find that tan theta is equal to mr omega square upon mg, so which will be equal to r omega square upon g, right? Now if you observe the figure, then tan theta can also be represented as r by h, because here if you see, this is theta, so tan theta is r by h, right? You can see this r by h, tan theta can also be mentioned as r by h, right? So now, so can I go down?
Yes, sir. Yeah.
So now if you are having tan theta is equal to r omega square by g and r by h also, so you can equate this two. So from this what you will get is h is equal to g by omega square, and further if you write this omega as 2 pi n by 60, then you can write h is equal to g upon this 2 pi n by 60 square. If you take g is equal to 9.81, right, and this 2 pi by 60 can also be considered as constant. So if you put value of all this, right, then you can simplify it as h is equal to 895 upon n square meter, right? So this is the relation between the height of the governor and the speed. So you can see that h is proportional or inversely proportional to the speed of this particular fly ball, right? It is in rpm, but you can also write h is proportional to 1 upon omega square, right? So this is how you are having this this important relationship between the height of the governor and the rotational speed, right? So this is for watt governor. If you go for Porter governor, because see what happens is, in this particular equation h is equal to this 895 upon n square, if you plot the graph at higher speed, there is very less variation, right, in height. As the speed increases, then the displacement in the sleeve or the difference in height is very negligible. So you can see that at that particular higher speed, it is not possible to operate the throttle valve efficiently if h is not changing considerably with respect to change in speed. So in order to overcome this particular limitation, what is done is an extra mass is attached to the sleeve in Porter Governor, as you can see in this figure, right? So here in this figure, an extra mass m is attached to the sleeve, right? And here the frictional force is also considered. Mg plus or minus F is written. So when sleeve is going to move upward, that frictional force is going to help. So at that time it will be Mg plus F, and when this particular sleeve is going to move downward, at that time that frictional force is going to work in the upward direction. So at that time it will be Mg minus F. So this is how you will have this Mg plus or minus F by 2 acting at the sleeve, and they have considered only the half portion here. So here for Porter Governor, the only change is you have taken this particular extra mass on the sleeve. Now if you draw this what we can say, this this different velocities of different components, and then when you try to locate the eye center, you can find it at a particular point I as mentioned here. So once you have this geometry as mentioned in the figure, you can equate the moment about that point I of different forces, right? You are having different forces like the centrifugal force acting on the balls, then this particular this mg of that fly balls, right, which is acting downward here, and this particular extra mass m which you have added, right? And you are also considering frictional force. So if you consider moment of all these forces, right, sigma of moment about this I is equal to 0. If you consider this, then mr omega square into this distance a, right? So that is anti-clockwise, right? That is anti-clockwise, and the moment due to the other two forces mg and this mg plus or minus f by 2 is in the clockwise direction. So you can equate this, right? Anti-clockwise will be equal to clockwise, so it is nothing but sigma of moment about I is equal to 0. So this mg is having the distance c, and this mg plus or minus f by 2 will be having the distance c plus b, right? So if you further simplify this, then you can have this mr omega square is equal to mg c by a. One second. You can have this c by a plus this mg plus or minus f by 2, then c by a plus b by a. Now if you look at the figure, then your this c by a and b by a is tan theta and tan beta. From the geometry it is clear, right? This tan theta is c by a and tan beta is b by a. So from the geometry it is clear. So you can write that mr omega square is equal to mg tan theta plus mg plus or minus f by 2 tan theta plus tan beta, right? So now if you can take out the tan theta, right, then mr omega square is equal to tan theta, right, then mg plus or minus f by 2 in bracket 1 plus k, where your k is equal to tan beta by tan theta, right? So as we have already seen earlier, tan theta is r by h, right? So if you put tan theta is equal to r by h, then you can write that omega square is equal to 1 upon mh, right, into this, I am multiplying it with this 2, right, plus mg plus or minus f 1 plus k divided by 2, right? 2 mg, sorry. Right, so this is how you can write. Actually, I have multiplied and divided it by g also in the same step, right? You can consider it, because this m also I have taken inside, so it will be like this. So omega square can be given by this g by h, right? In bracket this 2 mg plus or minus f 1 plus k by 2 mg. So here again this omega square is equal to g by h is somewhat similar what we have seen in Watt governor. So omega square is equal to g by h can again be replaced with n square is equal to 895 by h, right? And you can take different cases, right? You can assume that k is equal to 1, it means tan beta is equal to tan theta. So right, if you take that, what will happen to this particular equation? Or you can consider that friction is 0, or you can consider both, that k is equal to 1 and f is equal to 0. So you can consider those special cases, and you can simplify this equation, right? So this is how you are having this relation in Porter governor. So if you go for Powell governor, then what they are doing is they are providing this they are extending this lower link, and on that they are providing this mass or fly ball, right? So in Powell governor, again you can take moment about this particular point I. So it will be mr dash omega square e is equal to this mg c plus r minus r dash, actually, right?
Sir, was there any problem with Porter governor?
Sorry,
Sir, was there any practical problem with Porter governor?
actually in case of Porter governor also, that mg plus f and this mg minus f, until and unless that particular force is not reached, your sleeve is not going to start move, right? So that is why sensitivity is also less in case of Porter governor also. So by extending this links, we can achieve somewhat higher that sensitiveness. So that is why if you write this equilibrium equation in case of Powell governor like this, and then you simplify it as we have simplified in the previous case, then what will you get is this. I am writing the final equation that n square is equal to 895 by h into a by e, right, where a is this distance and e is this whatever extra distance we have provided to those fly ball by extending the lower links. So a by e, and then this whatever we have already there in our previous derivation, it will be the same, right, divided by 2 mg. Right, so like this you can derive the relation between the speed and height of governor in case of Powell governor. So this a by e will allow you the movement of sleeve with what we can say less change in speed or something like that. Otherwise, until and unless certain speed is not achieved, that certain forces are not generated, right? And so you will have less sensitivity, right? So after this Powell, you are having the spring controlled governors. So in spring controlled governors, you are using this spring force, right? So here one of the spring control governor is Hartnell governor, right? So what happens in case of this Hartnell governor is, as you can see here, you are having again bell crank lever, in which at one end that fly balls are there, and at the other end that roller is there, right? So they have considered two different position, that position 1 and position 2. So sleeve is moving upward, so that is why they have considered this frictional force as plus F, right? As you can see, that frictional force is considered as plus F. So if you see the different forces acting, right, then again this the centrifugal force mr omega square, right, and this mg plus here fs1 and fs2 are the this spring force, right? So the spring force is added to mg plus f, which was there in that Porter governor. So if you again go for this equilibrium of moment, then here you can consider equilibrium of moment around point A. So if you write it for both the case, then you can write that F1 A1 is equal to this 1/2. We are again considering only half the portion, so you can consider this mg plus fs1 plus f into b1 plus this mg c1, right? This mg into c1, this mr omega square into a1, right? This f1 a1 is nothing but that mr omega square only, right? As you can see, f1 is there and f2 is there. mr1 omega 1 square, here actually 1 is written, but mr omega square is there. Similarly for f2 a2 also you can write that 1/2 is mg plus fs2 is f, this b2 plus mg c2. Right, now if you consider that this a1 a2 are equal almost, right, and this b1 b2 are almost equal, right, and you can consider c1 c2 are almost very negligible, so c1 c2 if you consider it as almost 0, right, and if you simplify, then you can write your f1a equals this 1/2 mg plus fs1 plus f into b. Similarly f2a is equal to 1/2 mg, this is capital mg, right, plus fs2 plus f into b, right? So now having this two equation, if you take subtraction, then this fs2 minus fs1 can be written as f2 minus f1, right, into 2a by b, right? This fs2 and fs1 are spring force, right? So spring force is nothing but whatever that stiffness of the spring, right, and the deflection. So actually this spring force can also be given by this h1 into s, right, because load per unit deflection is stiffness, right, is equal to load per unit deflection, right? So this load equal to then stiffness into deflection, so stiffness into deflection h1 into s can then be written as 2a by b f2 minus f1, right? So this is how you are having this relation in case of Hartnell Governor, right? So after that Hartnell Governor, you are having this Hartnell Governor.
Please show the audience.
1 second. Right, like this. Okay.
Okay, sir, done, sir.
Okay. So after that Hartnell Governor is there. So in Hartnell Governor, again it is a spring controlled governor, right? So you can see here they are having this spring ball attached to a frame with the help of this spring. So if you are going to write this equilibrium of moment in this particular governor, then you can have this F into A, again this centrifugal force into this distance equals to this S into A, where S is the spring force, right, and then mg by 2, here friction is not considered, right, mg by 2 into B. So your this S can be written as K delta, right? This is the spring force, you know, as it is given by K delta, so it will be represented as K into R minus R0, whatever initial radius, and from that whatever radius is achieved, right? And then F is again mr omega square. So by having this relation, you can again derive the relation between the speed and the height of the governor, or in this case actually not height, but you can have idea that what are the different parameters, or what are the different spring force at different speed, right? So this is the relation between the change in speed and the change in that spring force, right? So once you have that spring controlled governor, then you are having this Pickering governor. So actually this Pickering governor are having this 3 leaf spring, and they have attached one fly mass at the center of that leaf. So here only one leaf is shown. So you can see whenever this fly mass will have that centrifugal force, then what will happen, actually it will move away, right, by the distance that E plus delta, as it is mentioned in the figure. So if you see that this force, this centrifugal force which it is going to experience is nothing but me plus delta omega square. Now if you remember that in your strength of material you can have this delta of the simply supported beam. If you consider delta of simply supported beam deflection and in which your that load is applied at the center, then it is given by delta is equal to FL cube upon 192 EI, right? So if you consider this where I is given by the moment of inertia of that cross section of that spring, BT cube by 12, right? So this is how you can have this calculation of forces acting on that particular mass, right?
Sir, it's 48 EI, I think.
You may be having the different case, whatever we are considering. In that case, actually this deflection is WL cube upon or FL cube upon 192 EI, and this kind of governor is generally used in gramophones and all, right? Pickering governor. So finally let us go through some important terms of governor. So if you consider important terms or important things when you are dealing with governor, then it is this sensitiveness of a governor. Sensitiveness of a governor, right? So sensitiveness of governor means how your governor or how the sleeve movement is changing with respect to change in your speed, right? So it is mathematically given by that range of speed for which your governor is designed upon the mean speed, right? So range of speed may be given by this n max minus n mean or n2 minus n1 upon this mean speed n, where this mean speed is n1 plus n2 by 2. So you can write it as 2 n2 minus n1 upon n1 plus n2, right? So the sensitiveness of a governor is important thing. Through this you can have idea that how sensitive your governor is. So it means how the change of speed will result in the change of fuel supply, right? After that, the hunting of governor, right? Hunting of a governor. See, hunting of a governor means whenever your this fly ball will move away, right? As we have discussed, your fly balls will move away when the load is less, because speed is going to increase, and that is why that mr omega square will be experienced in what we can say increased amount, and that fly ball will move up. And so when that fly ball will move up, it will try to reduce the fuel supply so that it can again come back to equilibrium speed. But when it is doing so, during that course of time, if that fly ball will come to a position where again the speed is going to be reduced, right? So what will happen if the speed is reduced? Then fuel supply needs to be increased, right? Are you getting? So when your fly balls has moved up, the fuel supply is decreased, and it has decreased to that amount that again it has come below the equilibrium position, right? So if you see that in that figure which we have seen earlier, right, if you see in this figure, so if this is the equilibrium speed, and when the speed is increased, flyball will move upward, right? So the fuel supply will be decreased. So if it is decreased to such a manner that it will go below the equilibrium condition, right? So what will happen? Again it needs to be increased, and again if they will increase, then again if it will go above the equilibrium speed, then this cycle will keep on running, right? So if it happens so, then it is known as hunting of governor, right? So this is how this hunting of governor is an important phenomena in this governor, right?
Sir, is hunting good?
No, hunting is not good. It should be avoided, because otherwise your sleeve will gets wear, right? Because a continuous movement of sleeve will be there. It gets wear, and you cannot have that equilibrium speed, which is actually ideal, right? It should keep running at that equilibrium speed. So hunting of a governor should be avoided, right?
Okay, sir, I would ask a question that in sir present cars, sir, which type of governor is mostly used?
I guess this spring control governor may be there, but still I need to check, and I will get back to you if there is any other what we can say more advanced governor or something like that is used, right?
Okay, sir. Okay.
I will check it. So here isochronism is one more.
Sir,
Yes.
can hunting be quantified?
Sorry.
Sir, can hunting be quantified?
Hunting, I guess, actually you can quantify it for some of the governors, but you can have some certain condition. If you have those condition in your governor, then you can say your governor will have hunting. Yes, so it can be done, right? But we are not going into that detail for now, right? You can check it. As we have seen that relations in different governor, you can also come up with conditions at which hunting will take place, right?
Okay.
So if you go for the next term, that is isochronism, it means what happens is here you are having a range of speed as 0 in case of isochronism, right? So you can have different radii at the same speed, right? So isochronism is also not good for a governor, right? What is important is stability, right, is another term. So stability means, as I have already mentioned, when you are having that change in load, what will happen is you can change the fuel supply, and once you do that change in fuel supply, it should again settle down to that equilibrium speed without much hunting. So that is actually the what we can say, this stability of a governor, right? So
Sir, please repeat about isochronism.
so isochronism is, as I have told you, isochronism is a phenomena in a governor when this governor is having a range of speed 0, right? Which is not acceptable, actually it is not ideal, right? So now the next is effort of a governor. Now effort of a governor is actually, see, whenever you are having any change in speed, your sleeve is going to have that motion, right? So that whatever force is acting during that course of time, which is moving the sleeve and all, that is known as effort of a governor. So suppose if you take Porter governor, right, then let us say H is mentioned with this G by omega square plus that mg1 plus k 2m omega square, right? So now if you are changing the speed from omega to omega plus c omega, means you are changing the speed by c percentage. So your new speed will be omega plus c omega, right? And what will happen is certain effort is required, right? So whatever that dead weight is there, mg, it will have certain effort, that is mg plus e. So here that new h, right, can be written as that here what we are going to change, omega to omega plus c and mg to mg plus e, right? So this is how you can change it. So once you provide this particular changes, right, then you can calculate your effort, right? So if you calculate it, simplify it, you will find it as cg upon 1 plus k 2m plus m1 plus k, right? So this is how you can have your effort of a governor, right? So once you are done with effort of governor, you can also calculate the power of a governor. So power is actually, you know, that work done, right, per particular time, right? Rate of doing work is power. So work done is whatever effort you are applying, right, this e by 2 into the whatever sleeve movement is happened, and due to that change in height of governor will be there, right? So this is how your power of governor is mentioned, this whatever effort e by 2 into change in this height of governor. So this is how you are having your what we can say, this effort of a governor and power of a governor, right? And finally you can have idea about the controlling force, right? So controlling force is also required in a governor. So whenever you are having that centrifugal force acting on your governor, there must be some controlling force which is acting in order to keep that in equilibrium, right? So this is how you are having this different forces acting in your governor, right? And finally the last thing is actually one question was asked right in 2022 only, session 1. So you can try this question, it is a very easy question only. The figure shows a schematic of a simple watt governor mechanism with the spindle O1 O2 rotating at an angular velocity omega about a vertical axis. Now the balls at P and S have equal mass. Assume that there is no friction anywhere and all other components are massless and rigid. Now the vertical distance between the horizontal plane of rotation of the balls and the pivot O1 is denoted by h. The value of h is 400 mm at a certain omega. If omega is doubled, the value of h will be how much am, right? So it is very simple, I guess.
100.
Right. So there is a relation, right, between this h and omega square. We have seen, right, h is equal to g upon omega square. So you can write that h is proportional to, or we can say inversely proportional to the square of the speed. So if you are having h1 and h2, then you can write h1 upon h2 is equal to omega 2 square upon omega 1 square, right? So h1 is given as 400, h2 you have to calculate, omega 2 is given as 2 times omega 1, so 2 omega 1 square upon omega 1 square. So now if you simplify it, you will find h2 is equal to 100 mm, correct? So here you are having this 100 mm as the correct answer.